Hello, hello, hello. So long to see you, but I'm here to discuss some acid-base chemistry. Gonna discuss some acid-base chemistry. Okay, so I'm waiting on someone here to join in. Okay, all right, so this is Dr. Moses here. I feel like I should talk about acid-base chemistry. This is just general chemistry too. And today we'll be discussing how to find the pH of a weak acid. You know, it would be easy to find the pH of a strong acid, but when you're given a weak acid, what do? Now, if you're not aware what an acid is, let me give you an overview. So an acid is just a proton donor. Of course, proton is H+. HCl is an example. If you add HCl to H2O, what do you get? It completely breaks down or ionizes. So that's how you show ionization. The oxygen is taking the hydrogen, the chlorine falls off. Then you're gonna get H3O+. H2O turns to H3O plus because you gained this extra hydrogen and you get Cl minus. So this is an acid because it donated the extra proton to water. The water has accepted the proton, then it's a base. This is what we call the conjugate acid because it came from the base, and this is the conjugate base because it came from the parent acid. So here you see I'm using a full arrow now because I know the concentration of HCl will be the same as the concentration of water because of complete ionization. Okay, it's a strong acid, so I expect it to completely ionize. Okay, there's gonna be complete ionization. See, we are forming ions. So this guy here is a strong acid. Okay, HCl is a strong acid. It's strong acid. It completely ionizes. But the problem comes when you have a weak acid that does not completely ionize. So if I want to find the pH of HCl, I'll simply do pH equals to log concentration of the acid and get it because I know the concentration of the HCl is the same as concentration of the hydronium. Where there is weak acid, the concentration of the weak acid is not going to be equal to the concentration of the hydronium, so we have to use what we call ice charts. So again, an example of a weak acid is acetic acid. You see the Ka value, which is the ionization constant of acetic acid, is 1.8 times 10 to the power minus 5. This is very small, which means the acetic acid does not completely ionize. So you cannot use this formula directly. You have to use ice chart before you use this formula to get the pH. So for example, here you're asked to calculate the expected pH of 2 molar acetic acid. So you not automatically put 2 molar in this formula. Nope. You have to find the concentration of the hydronium because it's barely formed first before you use the formula of pH equals to negative log of H3O plus. Okay, so here is your acetic acid. Let's do the same thing and add it to water. So let's add it to water. So we pretend it's ionizing. So the H2O plays the role of a base. This, of course, plays the role of an acid. We know it's a weak acid. Because it does not completely ionize, we use equilibrium arrows. So that's an equilibrium arrow to show that this reaction goes back and forth. What you're gonna get is you're going to get the conjugate base from acetic acid after it lost the proton, and of course you're going to get hydronium. Okay, so this will be the conjugate acid, this will be the conjugate base that came from the acid. So this is not formed in lots of amounts, so you're not going to use this formula directly. We have to find the concentration of H3O plus before we apply the formula, because acetic acid is a weak acid. So we use ice charts, especially when you have weak acids and bases being partially ionized. So now that we know that, we're going to apply what we call the ice charts. So ice charts. So I stands for initial concentration. C stands for the change in concentration during this reaction. And then E stands for equilibrium concentration. So as the reaction proceeds, you're gonna get to an equilibrium, and that's the equilibrium concentration that we'll need to use, especially for the H3O plus, alongside this formula right here, pH equals to negative log H3O plus. We have to do that because this is a weak acid. So we are told that we have 2 molar acetic acid. So in the beginning, we have a concentration of 2 mole of acetic acid. Now, H2O plus does not ionize easily, so its concentration is going to be negligible. And in fact, we are given that the ionization constant of water is 1 times 10 to the power minus 14. So it barely ionizes. So we don't expect it to ionize to give us H2O plus. So its concentration is going to be negligible. Now, because this is a weak acid, we expect initially that it will not form any of the conjugate base, what we call an acetate. Okay, so it's going to be approximately 0 concentration as the experiment starts. And then, of course, we expect this also to be approximately 0 as the experiment starts. Okay, because we have not formed the acetate, and we don't expect the H3O plus to be formed from water, because water does not ionize easily. So as the process goes on, as the reaction goes on, the concentration of the acetic acid is going to change by a value we don't know. And because it's going to be consumed, let's assume that it's going to change by X molar. Like the concentration will reduce, the negative sign means the concentration will reduce by a value of X. And then we're going to assume that water will not change in concentration, because like I said, it's negligible. And then because this is going to be formed in the process, we're going to say this is going to be formed in X amount. So the concentration will increase by a value X, we don't know. And of course, the concentration of H3O plus will increase by an equal amount of X. Why is it X, X, X? The reason is we have a 1 to 1 to 1 ratio. If this was 2, if you balance the equation and hydronium turned out to be 2, then we put 2X here. But we are putting plus because these are products, they are being formed. You are putting negative here because these are reactants going to be consumed. So the equilibrium concentration will be given by the sum of the initial and the change. So it's going to be 2 molar plus negative X. Obviously, this will be 2 minus X. That will be the initial, the equilibrium concentration of acetic acid when this reaction has balanced. Okay, then again here will be negligible because, like we said, water is not ionizable. And then here we're going to add the initial plus the change. So this will be X. You're going to add these two. The initial plus the change is going to be X. So we're going to focus on the equilibrium concentrations in attempt to find the concentration of H3O plus that we'll use with the formula pH equals to negative log H3O plus to find the pH. Now that we know the equilibrium concentration, we're going to take advantage of ionization constant value that are given. We are told that the Ka, which is the ionization constant of acetic acid, is 1.8. This should be equal to the product of products, the product of concentration of products, and the product of the concentration of reactants at equilibrium. In this case, our products are acetate and H3O plus. Our concentrations are XX. We don't know, we are going to look for X. And then our reactants is H2O and weak acid. So H2O is a liquid, so its concentration will be taken to be 1, okay? And then the concentration of acetic acid, of course, at equilibrium is 2 minus X. So in other words, what I've done here to get this expression, I have the concentration of the acetate multiplied by the concentration of hydronium. Those are the products, divided by the concentration of acetic acid multiplied by the concentration of H2O. So like I say, the concentration of H2O is 1, okay? Because it's a liquid. Liquid and solids, they'll be the concentration taken to be 1. We ignore them in this equilibrium expression. So the concentration of acetate is X, you see it there. The concentration of H3O plus is X at equilibrium, you see it there. And then the concentration of acetic acid is 2 minus X, you see it there. So we need this expression to find the concentration of hydronium, so we can find the pH of this ionization reaction of acetic acid, which is asked in the question. We need to calculate the expected pH of 2 mole acetic acid given the Ka value. Okay, so now that we know that, we're going to take our 1.8 times 10 to the power minus 8. Is it minus 8 or minus 5? It's minus 5. Pardon me, it's minus 5. Okay, so we're going to take that number of Ka and equate it to x squared. X times x is x squared over 2 minus x. Now, one can solve this equation and make it a quadratic equation. But you know, quadratic equations are not easy to solve. So when it gets to this point, the best thing you can do for yourself is to try and see if you can ignore this x. By eyeball, I can see that the Ka value of acetic acid is very, very small. So I don't expect it to change, the concentration to change as much here. So I can easily say that 1.8 times 10 to the power minus 5 should be equal to x squared all over 2. This one will no longer be a quadratic equation whenever you're simplifying it. But you'll always get the same answer if you use quadratic equation or simplify, especially if the K value is small. Now, there's another way you can determine if you should ignore the x down there. You can use the expression. Let me see if I can get a pen here. So you can use the expression molarity of acid divided by the Ka value should be way greater than 100 to ignore the x in denominator. So let's use this test to see if it's safe to ignore that x. So the molarity of the acetic acid given in the question is 2 molar. Okay, it's 2 molar. So I'm going to divide it by the Ka to see if the answer I get is way greater than 100. 1.8 times 10 to the power minus 5. So if you do this test, you get that the answer is 55,555. Of course, this is way greater than 100. So according to this test, it's safe for me to ignore the x. If this ratio was less than 100, then I should not ignore it. I have to use the quadratic equation or factorization according to calculus. So now it's safe to ignore that, not the numerator, just the denominator. So I can use this and be very correct. There's another way to see that ignoring there was correct, ignoring x was correct, but we'll talk about that last. So let's solve for x to find the concentration of the hydronium in our ice chart. So if you continue with this math, the value of x should be equal to 6.00 times 10 to the power minus 3. Okay, now this happens to be the concentration of hydronium. Look, go back to your ice chart. You'll see that the hydronium H3O plus at equilibrium has a concentration of x. So once we solve for x, we are now ready to find the pH of this solution when acetic acid is dropped in water. So we can now use our normal equation, pH equals to negative log of the hydronium ion. So you'll see pH equals to negative log of 6.00 times 10 to the power minus 3, which happens to be the value of x we just solved for. And the pH will be 2.22. That will be the final answer. Okay. So you can see we've solved for the pH. Now, I want to prove to you again that it was safe to ignore this x. So you see 2 minus x will be equal to 2 minus 6.00 times 10 to the power minus 3. If you try to subtract this, you'll find that the answer is 1.994. So this means that subtracting x from 2 does not have much effect on 2. Subtracting x from 2 does not have much effect on 2. So it was okay to ignore it, to avoid too much complex calculations, and just use 2 in our solving process instead of 2 minus x. Of course, you can always use this ratio. If it's greater than 100, it's safe to ignore the x. So we have just answered this problem where you are required to solve for to calculate the pH of 2 molar acetic acid, which is a weak acid. If it was just a strong acid like HCl, if I was to find the pH of 2 molar HCl, all I'll do, I'll go directly and just put 2 there and find my answer, because this is a strong acid. But for weak acids, you have to use the ice chart. Ice meaning initial, change, and equilibrium. To find the concentration, use the ice chart to find the concentration of H2O plus at equilibrium, which in this case is X. After you find your X, now you can go ahead and use your formula, pH equals to negative log of hydronium, to get the answer. So same happens if you're finding the pH or pOH of a basic solution. Okay? So that's a good example on how to work out this problem. See you soon for another live.